In this lecture, I'm going to tell you about ideals in a partially ordered set. So let P be a poset, and here's the definition. A subset I of P is called an ideal if X belongs to I and Y less than or equal to X, this is the partial order in P, implies that Y belongs to I. Now, I've just used the term ideal. Sometimes this is called a lower ideal, and sometimes it's called a down set. So you can imagine that we could also have defined it the other way around. An upper ideal is a subset I in P, such that if X is in I and X is less than or equal to Y, then Y is in I. Okay, but we'll just be using lower ideals for the most part in this course. Okay, so here's a simple lemma about ideals. If I alpha, alpha in some indexing set is a family of ideals, then the union of this family, union alpha in I alpha is an ideal, and the intersection is an ideal. These are very easy to prove from the definition of an ideal, and I'll leave you to just think it through. Now, we can define a partially ordered set of structure on the set of all ideals in a poset. So this is usually denoted by JP. Let JP denote the set of all order ideals in P. I just use ideals in P. So order JP by inclusion. So the containment partial order. Now what we know is that JP is a lattice. Why? Because if we take two ideals, I and K, then you can show that their least upper bound is just their union, which we know is an ideal, and their greatest lower bound is their intersection. And so for this reason, JP is a lattice, and JP is called the lattice of order ideals of P. Let me give you some examples of this. So example 1. Just take P to be an anti-chain. Meaning to say that P is a partial order where X is less than or equal to Y, if and only if X is equal to Y. Then every subset is an order ideal. And so JP is just 2 to the power P, the power set of P. And its lattice, the partial order, is just containment as usual in the power set. Let's look at another example. Let's take P to be the non-negative integers with the usual linear order. Then you can show that the order ideals, well, there's the empty order ideal, that's always there. And then there's one order ideal for each element of n. I'll come to that in a moment. And there's the whole set n, which I will denote by infinity. So I'm claiming that, so this is a disjoint union of 3 sets. Maybe I should just say the singleton set consisting of the empty set, the natural numbers, and the singleton set consisting of infinity, where we'll say that empty is less than n for all n in n, and we'll say that n is less than infinity for all n in n. So this is the least element, this is the greatest element. And what do these correspond to? This of course corresponds to the empty set, which is clearly an order ideal, that's vacuously true. An element, a non-negative integer n in n, corresponds to this interval 0, n, interval in n. And infinity goes to just all of n. And the point is, I've defined this map from the right hand side to the left hand side, and this is surjective to see that what we need to show is that any order ideal in n is exactly one of these. So suppose you have an order ideal in n. If it's empty, well then it's empty. If it's non-empty, then there are two possibilities. Either it has a greatest element, let that greatest element be n, then the order ideal has to be the interval 0 to n. If it doesn't have a greatest element, then it contains all natural numbers. So this is pretty straightforward. Okay. Now let's talk about try to classify all the order ideals in a partially ordered set in some sense. So for this, it's helpful to talk about the ideal generated by a subset. So definition, let P be a poset and S any subset. Then we define IS, this is called the ideal generated by S. It's defined to be the intersection over all ideals of P which contain S. Let me just move this a little to the right. So it's the intersection of all ideals that contain S, and this in itself is an ideal. In fact, it is the smallest ideal containing S. Now, another thing that I will use is the notion of the set of maximal elements. So this is defined as the maximal elements of S, which means that you just treat S as an induced subposet of P and take the maximal elements of that subposet. So this turns out to be the set of all S in S, such that if T belongs to S and S is less than or equal to T, then S is equal to T. So there's no element greater than or equal to S in S except for S itself. Okay, now I'm ready to describe all the order ideals in a poset, or rather just move the problem to another problem. So the theorem is this. Let P be a finite poset. Then the functions, so we have on the one hand we have JP, and then we have anti-chains in P. An anti-chain is a subset of an anti-chain in P, I mean a subset of P such that the induced subposet on that subset is an anti-chain. And so how does it go? An ideal I goes to max I, and a subset S goes to IS, the ideal generated by S. These functions define bijection, a one-to-one correspondence between JP and anti-chains in S. Anti-chains in P. What I mean is that these are mutually inverse functions, and therefore these two sets are in bijection. So the only thing really to check is that, firstly, that if you take an ideal I, then its set of maximal elements is an anti-chain. In fact, it's true that if you take any subset S, then max S is always an anti-chain. And that's easy to see, because if S1 and S2 are both maximal in S, then you'd have, if you had S1 less than or equal to S2, then this definition of maxes would just say that S1 is equal to S2. So this set is always an anti-chain. And of course, if you take any subset S, you will get an ideal. And the only thing to check is that these two functions are mutual inverses. And I will leave this as an easy exercise for the student.